class. Welcome to the next section, chapter 10.3. Here we're going to talk about applications to physics and engineering. We're going to discuss hydrostatic pressure. So, hydrostatic force is the force of water on a submerged object. Okay. The force on a submerged object is mass times gravity. It's a force, right? So mass times the gravitational constant, where here mass can be found as the density times the volume. So in volume, we know is area times depth, basically. So I can rewrite my force into its most basic pieces, which is the gravitational constant, the density of the object, in this case, water, the area that's being affected, and the depth above it. Okay, so here m is mass, g is our acceleration due to gravity, rho is density, which is measured in kilograms per meter cubed, v is volume, a is the exposed surface area. So very important that we're talking about the exposed surface area here. And d is the depth of that exposed area. And so if you're standing underwater, okay, you are at some depth d, and there is a column of water above your body that has some sort of mass. The water over here on the sides of you, they do play a part, but not really, right? So you're really only feeling the weight of the water above you when you go into the water, right? So that's why if you go very, 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 very deep, you have a large column of water above you, and it squeezes down and puts pressure on you. Okay. So the column of water above our object of interest is the mass, m, that we use in our calculations. The pressure is per unit of area, right? So our pressure is the force divided by the area. That way we're looking at pounds per meter cubed or inches squared or whatever the area is, okay? So if we were to take this force and divide out the area, we would just get the gravitational constant, the density, and the depth. So the unit of measurement for pressure is pascals. 1 Pascal is 1 Newton meter squared. Okay? The unit notation for Pascal is PA. So let's remember that the gravitational constant is 9.8 meters per second squared. There's more values here if you want to get more accurate, but generally 9.8 is all that's used. The density of water is 100 kilograms per meter cubed. Delta is the gravitational constant times the density. So for us, that's 62.5 pounds per foot cubed. So this is us using the weight of water. Okay. So let's do this customary unit. So it's the weight density, which is our density times the gravitational constant. So let's go ahead and use this information, right? Most of it was just talking about notation in units and our values that we'll be plugging in for constants. So for an example, let's find the hydrostatic force on the side, one side of a plate. Okay, so let's say that we took a plate, we dumped it into water. This plate is only partially submerged. The entire thing is not underwater, just a portion of it. Okay, so since we're using meters, it should make sense that we should use the uh, rho density of water. Okay, since it's already given to us in meters squared, it wouldn't make sense to use the weight 62.5 pounds per feet cubed, um, because then we'd have to change things anyways back into this, okay, or vice versa. So we're going to calculate the force on a slice, right? See here the slice of height delta y that runs parallel, right? Because the force on all of this strip is the same because it's all at the same depth, right? I would not take a slice up and down and try to find the uh, hydrostatic force on the up and down slice, right? It should be left and right because it's all at the same depth. So we're going to find the force on a slice, and then we integrate that function across the entire bounds of submersion. So in this case, I'm only submerged up to 4 meters, so I would just integrate over 0 to 4. Okay. Note that for us, the depth is usually distance from the top of the water. Okay. So from 0 to 4. So to make things easier, let's overlay an X and Y axis. That way we can start to mark things off, and then we can use the axis to help us find out some values that we need, okay? So if we put the axis so that the x-axis aligns with the bottom of the plate rather than with the bottom of my pool or whatever tank, whatever it is I'm using, it'll be more useful for me, okay? Um, Notice that our semicircle there has a radius of 6 meters. So if we make an equation for that, it would be x squared plus y squared equals 36, right? This is the equation of a circle. And then when we solve for either x or y, we generally get an equation that has a plus and a minus part, and we would just need to use the plus part, right? So that makes it really nice. So here we have a semicircle, radius 6 because the entire thing is 12. It is only partially submerged to 4 meters, okay? Our slices go in the x direction. So I can use x equals square root 36 minus y squared. You see, I'm only using the positive part because if I said plus and minus, I would be looking at the semicircle part. But the plus and minus, I mean, one already goes through the entire equation. So the plus and minus part is just kind of one goes to top, one goes to bottom. Okay. So for our semicircle, we can find the length of a slice now, okay? Remember, this x value is only half, okay? This is not the entire thing. It's just a distance from 0 outwards, okay? The negative part will give me this half right here, okay? So this semicircle is really only looking here. So the area of a strip is two of those, right? The one side and the other side, so 2 times x times the delta y. So this small infinitesimal height times this width, right, which is the radius times 2, so 2x. So when I substitute everything in, you can see I have 2 square root 36 minus y squared delta y, which is nice because that is going to be my differential of y for my integral. The hydrostatic force on the slice is force of gravity, the density, the area, and the depth. Okay, so we have the area so far. So for area of a strip, we're using um, the 2 radii, right? The radius twice times the height of delta y. G is a constant, rho is a constant, so I really only need a function for V. Okay, so gravitational constant is 9.8. Density of water, since we're in meters, we'll use the 1,000 meters per 1,000 kilograms per meter cubed. And my area is this 2 times x delta y. And so my depth here, right, I didn't write in the exact order because I like delta y at the end for one and square root kind of at the back also. So 4 minus y, right? 4 minus y means that anywhere in between here, I could say it's y, right? Or I can say that it's 4 minus y, right? 4 minus whatever it is that I'm at. So one will make more sense than the other. The two equations, the equation for depth and the equation for the radius at that depth, both have to make sense. So what I like to do is I like to check the bounds of what I'm integrating over, 0 to 4, and I'll plug in the two endpoints, right? So if I plug in 0, then for my equation 4 minus y, I'm going to have 4. I'll be at the top of the plate, okay? Um, I'm sorry, it gives me a depth of 4, right? Because now I'm talking about depth. So depth here would be 0, and then this would be 4. So 4, and then minus whatever my y is. So when I plug in 0 for x, my depth is at 4. Okay. Oops, further that. Okay. And then when I plug in 0 to my equation for the radius, I get square root 36, right, which is 6. So meaning when I have a depth of 4, that my radius is 6, which makes sense because from the top of the water, a depth of 4 meters, my radius is this entire thing. Okay, it's the whole one side. And so to get the whole thing, I would double that and get the 12. Right? So that kind of checks out for me. When I look at the bigger portion of it, y is 4. Okay, so when y is 4, that means I should be at the top of the water. And 4 minus 4 gives me 0, so I have a depth of 0. Okay, the top of the water. And then when I plug in 4 here, I get 36 minus 16, which is some number smaller than 6, which makes sense because remember, I'm only partially submerged. So at the top, it's not a radius of 0, but it should be a value more than 6. So y equals 4 gives me a depth of 0 and a radii of something smaller than 6. So my uh, e- two parts kind of line up when I plug in y is 0 and y is 4 here. The radius portion of it coincides with what I need my model to do, right? So that's a good way for me to check to make sure my model looks good, because if my model doesn't look good and I integrate, I'm going to get the wrong answer. And then I got to go back and fix my model, which means I just did a bunch of integration for nothing, right? So I'm fairly confident in my model here. I'll just go ahead and multiply all of this out. So that's 9.8 times 2 times 1,000. So that is this 19.6 you see here. The 4 minus y stays, and then this stays the same as well. If I try to integrate from here, that'll be rather difficult because any u sub that I make um, won't work for both of these. Um, I could say I could try to do, in fact, here would probably need a trig sub because it's something squared plus or minus something squared, or just a number plus or minus something squared. So that would be one of those trig subs. Um, in this case, minus. I don't remember if we're using tangents for that, or if we would be using one of the sines or cosines for that, right? But either way, that's what would be working here. A u sub here wouldn't necessarily be super helpful for me here either. Okay, I could go for it though. So what I'm going to do instead is I'm just going to separate this to two integrals, right? All of that just to say, let's just make these two different things, two different cases for me to work on. So I'll take this 19,600, I'll multiply it times 4, okay, which gives me this term here. And that multiplies times my root 36 minus y squared. I do the same thing and I multiply it times this, which multiplies times this one. So that's just a standard 19,600 being subtracted with the y on the inside. So basically all I did was distribute um, this across, right? This as a constant and this as a constant, and I distributed across this 4 minus y. So now I have two separate integrals, okay? One here and one here, which we'll see we have to evaluate differently for both, right? So here, something squared minus something squared, it's going to be the sign substitution, okay? I'm going to use the root of whatever was here. So that's 6, differentiate both sides, and so forth, okay? The way this works is in line, so let's go ahead and finish talking about what we're going to do over here. Over here, I could do the same thing, but with this y on the outside, that would get a little bit messy. This one actually works well with the u substitution because when I differentiate the inside term here, I end up with y something dy. So it actually will work very well. Let's differentiate both sides here, dy. Here, this will be 6 cosine theta, d theta. Here we get the du. This will be negative 2y dy, which is nice because I have a dy and I have a y. So the only thing I really need to work on is this negative 2. I could put it in here, but it'll be easier to just divide it both sides because that's exactly what I would be doing anyways. And so now we can substitute everything in. So again, notice that the integrals are almost identical. The only difference is that this one has an extra y on the outside and this one doesn't. So here I got to use one of my trig substitutions. Here I need to use a u substitution. Okay. So I'm plugging in all this stuff here. This is going to turn into a 6 that gets pulled out, and 1 minus sine squared theta on the inside, okay, for this y squared. Cosine theta and a 6 is on the outside. Here, I'm going to have negative 1/2 du, and this is just going to be u to the 1/2. Okay. Here, 1 minus sine squared is cosine squared under a square root, which is cosine times another cosine, so that's cosine squared. Here, I have taken 78 for 1,000, or 400, I'm sorry, multiplied it times 36, so this is where this 2 million and some change comes from. Here, I can just multiply this 1/2 through, okay? And everything else is the same. Notice I'm keeping everything in y so I don't get confused. Again, if you don't like to do that, if you'd rather change to theta equals and u equals, go ahead and do that. So the first half here, we're going to have to make a substitution. Remember, for cosine squared, we have to use the half angle theorem. So I divide everything by half for that half angle theorem, right? Half of 1 plus cosine 2 theta. And then now I can integrate this. I can make the substitution u equals 2 theta and go ahead and integrate that. But we know how that works. I end up with the 1/2 on the outside times the change of integral of cosine. So the 1 turns into a theta for me here. This goes to 3/2 and then multiplied by the reciprocal. I'm going to evaluate both bounds at 4 and 0. So let's go ahead and substitute things back in for the u. Here for theta, I have to make a substitution also and a triangle. So here I subbed in my u values. Okay. Here I made an equivalency for another half angle theorem. So 1/2 sine 2 theta is the same as sine theta cosine theta. So which will be easier once I start to form this triangle. I could still use the 1/2 sine 2 theta, but this is probably going to be easier. So let's go ahead and build a triangle from this. Before we build the triangle for this, we can solve for theta. So I would divide by 6 on both sides and then take the inverse. So sine inverse y over 6 is equal to theta. When I build my triangle is coming from sine theta equals y over 6. So for my angle, the opposite is y over the hypotenuse of 6. Then when I solve for the missing adjacent side, it's the Pythagorean theorem, right? So I would square this, added together is this squared. So in order to solve, I just go the opposite direction. Okay? You guys should be able to follow that on some scratch or even look at it and be like, yeah, that's right. So now that I have this, I can use these values and plug them in for my sine of theta and cosine of theta using the triangle. Theta I already know, and I'll be evaluating this at 4 and 0. Okay, so I have this 1 million and some change here. Theta we know is sine inverse y over 6, but my starting y is 4. 4 over 6 is 2/3. Right, so as you can see, we're kind of doing a few steps at once because this is a long problem, and this is calculus 2. So make sure you're working this with some scratch paper with you. Here we have sine theta. So sine theta we know is y over 6, and y over 6 for us is 4 over 6, or 2/3. And then cosine theta, which is this root over 6. And since I'm using 4, 36 minus 4 squared is 20, right? 36 minus 16. So I have my root 20 over the hypotenuse. Okay. For this form over here, we'll do the same thing. We'll have 36 minus 4 squared, which is 20. And we'll have the 0 portion as well. 36 minus 0 is just 36. Okay. This stays on the outside. This stays on the outside. Okay. So from here, we're just going to be simplifying. From previous videos, we saw that this is the square root of 20 cubed. This is the square root of 36 cubed. So I can pull out a whole 20, and one of the 20s stays inside of the square root. Same thing here. Okay. Here I can start to simplify. This 2 over 6 will turn into 1 over 3. And I have a square root 20, which is the same thing as square root 4 times square root 5. So I can get a 2 out of that. Okay. And so this 3 and 3 turns into 9. I got an extra 2 that came out of the 20. And a root 5 that didn't have a buddy to pull itself out. Over here, again, 20 squared is just 20 on the outside with that extra 20 on the inside. Same thing here. Here, square root of 20, we know is 2 times root 5. So I can multiply this times 2 and just leave this as a root 5. We know square root of 36 is 6. So we have 36 times 6 here. We have 20 times 2 with a root 5 left over. Okay. And so then from here, what I would like to do is try to simplify some more. You see here I have a root 5 and I have a root 5. So I can start to kind of, what I'm basically going to do is multiply this across everything and pull out some kind of factors, but we're going to do it just a little bit more slicker than that. This root 5 has 2 over 9 times this million something. This root 5 has 19,600 over 3 times 40. And so if I pull out the root 5 and leave all this other values on the inside, this is what it looks like. Everything left over is here. This 1 million and some change times the sine inverse function. You might say, well, how did this -1 come? 216 times 196,000 over 3 actually simplifies to 1,411,200. So that's nice because then I have a common term that I just factored out. Okay. Now, I can continue to go more, right? I can make this a common term over 3 and yada, yada, yada. But really, as an answer, sorry about that, as an answer, this doesn't make any sense. So we would just go ahead and talk about how many newtons it is, because that's the answer we want. Okay. I left 4 decimals of accuracy, but you can leave it to the general rule is 1 more than the decimal, the most accurate decimal that's given to you. In this case, 9.8 is what is the most accurate value that we're using. It's 1 decimal place. So typically what we do is that we would leave 2 decimal places of accuracy, but I generally leave 4 just because it's very accurate and you can do what you want with it after that. Okay. So then this would be my answer. This is how many newtons of force we would have on that plate. Okay. Let's do one more example. This is a very, very, very big example. So if you need to pause the video now to take a breath, get a piece of paper, because there's a lot of math that we're going to do. Make sure you're looking at your write-up form for this as well, if you're a student in my class, so that you can follow along. Would be great. It'd probably be better for you to actually write this as we go. Hopefully that's what you do with all these videos, but definitely have some pencil and paper ready for you. Okay, go ahead and get started. So we have a dam that has a 30-degree incline from the vertical. Okay? And it has the shape of an isosceles trapezoid. I'll just show you what that is. Um, the isosceles trapezoid is 100 feet wide at the top and 50 feet wide at the bottom. Okay? The slant height is 70 feet. Okay? So when it's slanted, it has a length of 70 feet. So we want to find the hydrostatic force on the dam when it is full of water. Okay? So let's first draw a picture from the side profile. So this is the lake or whatever we have. This is the face of the dam, and we want to find the hydrostatic force on this face of the dam. So the dam is full of water. Okay, we put an axis here, X and Y. We'll actually be doing this a few times, or as we break this down into pieces. Um, from the vertical, it's slanted forward 30 degrees. Okay. This is the height or the depth of the water. Okay. A slice of Y would look like this. So notice that a slice on the dam isn't necessarily the same as a slice here, right? Like it's got a different sort of shape to it, which we have to take into consideration. So let's briefly look at a generalized triangle that's going to be very, very helpful for us throughout all of these calculations, okay? Which is just a general 30-degree right angle triangle, okay? 30, 60, 90. We're going to use this everywhere because I'm slanted at 30 degrees. So everything I do is going to have some sort of a slant to it to some extent. So for a general 30, 60, 90, we know the hypotenuse is always 1. Okay. We know that this adjacent side is root 3 over 2, and the big side is 1/2, right? So um, this is the way our 30, 60, 90 triangles always look for us. We need to consider going up a height of y. Okay, so my root 3 over 2 is going to change to y. So how do I get from root 3 over 2 to y? I have to divide, or let's say multiply, by the reciprocal of this. So if I multiply this times 2 over root 3y, I will get just the y will remain. That means in order to figure out these other sides, I'm going to multiply everything by the same exact value. My triangle multiplies its scales, right, by the same factor. So this has to get multiplied by 2 over root 3, and this has to get multiplied by 2 over root 3. So if we do that, right, or multiply or divide by that uh, root 3 over 2, right? It's the same thing. So I'm going to get 1 divided by root 3 over 2 is the same as the reciprocal, 2 over root 3. That opposite side, the one that's not known, that 1/2, I'll divide that by root 3 over 2 as well, and I get 1 over root 3. So my new triangle, my reference triangle that's going to be very useful is now y, 2 over 3 root 3y, okay, and 1/3 root 3y. Okay. Some of you might say, oh no, I call this root 3 over 3, and then this is 2 root 3 over 3, so it's the same thing, right? So this is going to be very useful for us. So next thing we want to do is let's look at the face of the dam. So if we were standing straight on. So far we have a picture where we're looking um, from the side. So what we're going to do is we're going to pretend we're right here and looking at the face of the dam head on, right? So this is a three-dimensional object that we're taking a slice in on one side in one direction and a slice in the other direction to look at, right? Not for calculations. Well, for both. So the face of the dam looks like this. Okay, we have 50, we have 100, and the slant length is 70 feet. So, okay, the slant height is 70. So the length of the slant is 70 feet. So I want to know the length of the dam from the bottom to the top of the water. So how far is this, basically? I want to know what this length is. Okay, it's going to be useful for me for my calculations. So that's what L would be, right? From top to bottom of the face of the dam is the same as the top to the bottom of the face of the dam. So I need to know what that height is. We're going to call it L, okay? L is from the top of the dam to the bottom of the dam, or vice versa. My slice is going to go across the face of the dam, right? It's still going to go across the face of the dam. It's just not a straight line. It's a straight line, but it's a slanted line, okay? So note that the height of the strip here, or the distance of the strip is not delta y, right? Because it's at a slanted angle. It's at an angle. So HS, right, this length here is not the same as delta y because we're looking at the face of the dam. It looks flush and parallel with us. So our integral will go from the bottom of the water to the top of the water because I'm 0 and this is the top of the water. Okay, and again, notice that this length delta H is not the same as the distance of the slant inside of delta H. That slice we're going to take. So from 0 to H. So in order to find the value of H, I need to find L first. Okay, so again, coming back, what I'm going to do is I don't have anything labeled here, right? I labeled everything I had. I don't know this height. I don't know this face length, right? But on the face of the dam, I know a bunch of stuff. So all I really need to do is find one side, and then I could use cosine of 30 degrees, sine of 30 degrees, or tan of 30 degrees to find this side or this side. Once I find this, especially since this is considered my hypotenuse for this triangle, right? So what I want to do is, if I can find this length here from the bottom to the top of the face of the dam, I could use that with this 30 degrees to find any of these other things, specifically this height. Because remember, height is, for this angle, adjacent over hypotenuse, right? So if I find this length, all I need to do is, I have enough information then to find the height here. Okay? All right. So in order to find the value of H, the depth of the water, I need to find the value of L, the length of the face of the dam. Okay. So what I'm going to do is I'm going to draw some reference triangles to find the length of the dam. So this dam height is L, right? The length from the bottom to the top. The slant length is 70 in length. And then this is 25. And they say, how do you know that's 25? Well, I got 50 here, and this is 100. So that means this half and this half have to add up to 50. So half of that is 25, right? So I'm just looking at this one triangle. I got a length of L here, slant length of 70, and this length right here is 25. Okay? So that's going to be my reference triangle. In order to find L, I again just use the Pythagorean theorem. So square this and square this, and I find the distance between them and square root it. Okay, so that's square root 4275, and then that exact value is 15 root 19. So we will be using this exact value so we do not get a decimal approximation error in our final step. Okay, so we always, always, always use exact values as long as possible. So 15 root 19 is the length. So now that I know the length of this, I can find the height of my dam, right? Because now I have this side length. It's 15 root 19. So, okay, if we look at the triangle I have now, it's 30 degrees, height of h, and the slant face length was 15 root 19. In order for me to find h, I just make some equivalencies here. So cosine of 30 degrees for this triangle is adjacent over hypotenuse. Okay. We also know that cosine of 30 degrees from my triangle way back here, okay, is root 3 over 2 over 1. Okay. So here we go. Root 3 over 2 is equal to this h over 15 root 19. I need to find h. That's what I'm looking for. So really all I have to do is multiply both sides by 15 root 19. And I get 15 over 2 root 57. So 3 times 19 is 57. 3 and 19 are prime, so I know 57 is prime. And then this 15 is over the 2. Okay. So now I know what my value of h is. So remember that force is g times rho times the surface area of exposure times the depth. Okay. We also know that G times rho is the same thing as that sigma, right? That weight density. So for the area of a strip, especially if we come back here, we're using feet. So we would not use 1,000 kilograms per meter cubed for the density of water. We would use that 62.5 foot-pounds. Okay, right. So the area of a strip then, now that I know my height, now that I know this length, I can find this area of the strip much more easily. Um, my reference triangle now looks like this. 15 root 19. Again, remember that's the length right here. That dam face is 15 root 19. So 15 root 19 is this length. This side is 25. The slant length is 70. And then we just have a length of W in the middle of one of these triangles, I'm sorry. So let's now just solve for W. So we need similar triangles. So W is uh, over 25 is the same ratio as this height to the total height, or this slant length to the total slant length. So we have a choice. Let's go ahead and go with the height because we can pull this from a reference triangle, right? Remember, if I'm coming up distance here, the 2/3 over √3 comes from that reference triangle I had in the beginning. Okay, so let's just kind of look at this. So remember that my dam face is angled at 30 degrees. So this isn't just the height of y, because this face of the dam is slanted. So the y that goes for this is relative to that 30-degree slant. So remember, for a standard 30-degree triangle, this is what I had. I had y 1/3 √3 over y, and the slant length was this 2/3 √3 over y. The slant length is going to be the same as this height, because remember, the dam is slanted, right? So anywhere up here at a height of y going straight up and down has an actual face along the dam length of 2/3 √3y. Again, if I come back to the original, if I'm coming up a length of y, okay, then the actual length along the dam face from 0 to the top here, right? The length of L has this length here, which again we found here with this reference triangle, right? So y, and then back there, this is it, y, and this is the length that we're looking at. Okay, so since we're along the face of the dam, it's not y, it's that slant length along the face of the dam. And again, this is we already got this point, okay? And so I'm going to make my reference triangles. So W over 25 is the same as this thing over this thing, or vice versa. It doesn't really matter which order, right? So W over 25. So we're putting the small triangle stuff on top, big triangle stuff on bottom. And really what I'm trying to do here is I'm trying to isolate W, right? Because what I'm trying to find is the area of a strip. So I know I have 50, I have a W, and another W for the length of each strip, right? And then I got to find what this HS is, and that'll be the height times um, the width, and there we go. So 50 plus 2 W's. So what I need is I need to solve for W, right? So I just multiply both things by 25 and then start to simplify this, meaning that 3 comes to the denominator, okay? And I'm multiplying times 25 here. So 25 times 2 is my 50. 3 moves down to the bottom. So that's 3 and 15. And then this 19 comes from me rationalizing the denominator. Okay, so I'm going to multiply it by square root 19, top and bottom. So I get 19 on the bottom and 3 times 19 under the square root, which is nice because other things that I have, like H and L, okay, H has a square root 57. L does have a square root 19 in it, but it's nice when I have things appear in different places. So if we finish simplifying, this 15 and the 50 can simplify. If I pull out 5, I get 10 on top and 3 on bottom. So 3 and 3 is a 9. And so from here, there's nothing else I can simplify. So I would just multiply everything out. So 9 times 19 is 171. Now you might be like, well, where did this come from? Well, it's 20 because remember, I need 2 W's and a 50. So my total width across is 2 times the W that I found plus the 50 that was in the middle. One of the W's, the other W, 50 in the middle. Okay. And 1 W is 10 over 171 root 57. So 2 of those, so I double it plus the 50 in the middle. Okay. Again, remember that little slice on the horizontal is not the same as delta y because the dam is 30 degrees forward. So it's not the same as the change in y on the vertical, right? So we have a height of 15 over 2 root 57, just in case you need to remember what our height was here. Okay, the dam height was the length of the face is 15 root 19. The dam height itself from the top depth-wise is 15 over 2 root 57. So, okay, when we're looking at a change in y, that creates on the face of our dam a slanted line, okay, which is actually larger in value than our vertical change that we would normally consider. Okay, so we use that same reference triangle that we created earlier. Okay, but instead of y, I'm using delta y, but everything's the same. This is root 3 over 3 delta y, and this is 2 root 3 over 3 delta y. Okay, so this face length, this height of the strip that we have along the face is given by this value. So the height of a strip is 2/3 root 3 delta y. So now I have the height of the strip along the face, and I have the width, right? So again, remember there's the 50 and then the two w's. So when I put this all together, 2 root 3, and the delta y, and then my width. So now I have the slices along the entire face, right? When I take my integral from 0 to the top, depth-wise, but what I don't have is the depth. So this delta y, it's a distance of y less than 15 over 2 root 57. So what is the depth? So if I go up to here, how much is left? What is the depth at this point? It's the total minus how much have I already come up already. So 15 over 2 root 57 minus y is the depth of each slice. Okay. So now I have enough to throw everything together. I got my slice. I got the hydrostatic force on that slice on the face. So now I just have to put it all together. 0 to 15 over 2 root 57. The pressure of water. This is again from that slant face from the delta y. This is the width, okay? And then this is my depth. So the easiest way to deal with this, obviously, is to multiply everything out. Remember that these are just constants. Here, I would like to just kind of multiply this across to make everything easier. Remember that the 171 is 9 times 19. I just like remembering how I count numbers so that if I can do it without having to punch in the calculator and just cancel stuff, that's always easier. And then I just play with much smaller numbers, okay? I remember that 57 is the same as 3 times 19. So all of that should come in handy as I work through my problem. So uh, everything kind of gets messed up sometimes. This is a very long line, so that's why you see the equal sign up here on your actual write-up or in the course reader. Once it's all finished, it will all be formatted a little bit nicer than I'm able to format for these presentations sometimes. So anyways, let's go ahead and get started. Here I have 62.5. If I double that, that's 125. And then I just wrote it over 2. So I basically took this and turned it into a fraction because it'll be easier to deal with than decimals as I work through. I'll multiply that times this same thing here. Then here, maybe we're going to start multiplying everything by, right? So I'm going to have 20 times 15, 171 times 2. So 2 and 20 cancel. That's where this 10 is from. I know 171 is 9 and 19. And I have my 15 left over. And this 57 is coming from root 57, root 57. So from here, I'll be looking for anything else I can cancel. Probably this 57, because remember, this is 3 times 19. So there's a 19 here that can cancel, and a 3 here can cancel. Also, 15 and 9 have a 3 in common. So if I can't get rid of everything, I'll be able to get rid of more stuff. Okay. The next term, I'm going to take this times negative y. So there's nothing really for me to do there. Okay. Except for square the y. Apologies, I didn't even see that. Now I multiply the next two, 50 times this, so I know 15 over 2 is 25. So I basically get 25 times 15, okay, which is basically 3 times 5. So this is actually a 5 cubed times 3, which I can start to simplify later if I need to. I have my 57 here, and so the last term is just negative 50y. Okay. So slowly but surely, I'm trying to like simplify stuff. Here I have 2 over 2, so that's nice. These will cancel. And I have 125 over 3 root 3. I'm looking to see if there's anything in here I can combine, like term-wise. We already saw I can start to cancel stuff here. And it goes with 50, so that's nice. Those are two y's. This is just a constant, and then this is just y squared, so that can't simplify. So just trying to look ahead a little bit. Um, so here, this 57, I know is 3 and 19, so the 19s cancel. This 3 cancels, it means this 3. That cancels with this 3, which leaves just 10 and 5 or 50, which is nice because there's a negative 50 over here. Over here, I can't really do anything yet. With this, I can rewrite this as 5 cubed times 3, or just multiply it all out, times root 57, and this is also just negative 50. Okay. So next thing I can do, obviously, is get rid of this 50y. Okay. And then it looks like I got rid of the 50y, and at the same time, with the two things that were left, I pulled out a common denominator, okay, or a common term. So they both have root 57. So you can see I pulled out root 57. They are both multiples of 5. So I can pull out 5 from here leaves me 4. So again, I have pulled out a 5 and a root 57 because that's what's common. Here, if I pull out 5, I'm left with 75. Okay, so that's nice to know. Um, and again, you can see that here. Let's say I pulled out a 5 from this. I would have 25 times 3 left over, so that's 75. So again, having things factored keeps it easy for me to do math if I start pulling things apart using my algebra brain. So for the next line here, um, you see that the 125 and the 5 gets multiplied. I know 57 is root 3 times root 19. So the two threes turn into a real 3 and cancel with this one. I'm left with root 19. Okay. And from here, I'm ready to integrate because this is just binomial quadratic. This is just constants, right? So I don't have to actually multiply these out. I just throw them in front. Um, but remember, this is 5 cubed. So with this 5 here, that actually makes it 5 to the fourth power. Okay, if I decide to put this into that form. Here, remember, I know 171 is 9 and 19. So when I integrate, this turns into a 2, I'm sorry, to a 3. It gets multiplied as a denominator for the constant value. This just gains a y, and I am going to evaluate at 15 over 2, root 57 to 0. Notice that when I plug in 0, the whole thing goes to 0 here. So I really only have to look at what happens when I plug in 15 over 2, root 57. Okay, so I'll do that for the cubed and the y. And we'll start to try to simplify things. Okay, so this 319, I just went ahead and multiplied to 57 because I know I'm going to have a root 57 coming in here and it's going to be cubed. So I'm sure one of those will get pulled out in that case. So for my cube term, it's 15 over 2, root 57. Again, remember this, I'll have a 57 that pulls out and one left in under the square root for whenever I have something cubed. Here, I'm multiplying this times 75. 2 doesn't do anything for either of these terms, which is fine, or nor does it do anything out here. So I'll probably end up with these halves here no matter what. But you can also see that they're also common on both terms eventually. So let's continue to simplify stuff. I have a 15 cubed, as you can see here. 2 cubed is just 8. One of those 57s gets pulled out, as you see, so I'm ready to cancel that out at some point. And here, I haven't done anything else. Okay. So again, the first part I'm leaving the same. Here I canceled the 4 and the 8 to give me 2 on the bottom. I canceled those 57s. I have 15 cubed left on top with the 9. Here I just pulled out the 1/2 so I can get things to look a little more linear. And so then on the next slide, let's go ahead and multiply in this root 19. Um, because here we know that both of these are root 3 times root 19. So I get to pull out a 19 out of both of these and leave a root 3 on the inside, which will be nice. Okay. Let's see, what do I do here? It looks like I pulled out a 5 squared from the top. So I didn't multiply in the root 19 yet, but I did separate 15 squared to be 115 and a 25. So this is 3 times 5 times 3 times 5 times 3 times 5. So if I separate all of those terms out, I get this negative 5. So 3 gets to cancel with the 9 that used to be here on the bottom. Okay. So I had here a 9. So if I pull out 2 of the 3's, I'm left with 2 5's that are no longer paired with the 3. And then there's one 15. Right. So I have one lone 15 and a 5 squared. And this 2 on the bottom, which I can pull out as 1/2. Okay. So now I have a 1/2 on both of these. I got a 15 on both, and I got a 25 on both, and a root 57 on both, right? So I can pull out some more terms, and I'm left with pretty much just -1 plus 3 after that, right? So if I pulled out the 25s, I pulled out the 1/2, I pulled out the 15, so the only thing that's left is this -1. On this side, the only thing that's left is that 3 from the 75. So we know that adds up to 2, which is multiplied here, which gets rid of that 1/2 at some point. And so I have a lot of values here, okay? These 19s get to cancel out to a single 19, and I'm left with a root 3. So this is, what do I have? I got 3, 4, 5, 6, 7. So I got 5 to the 7th power, and the 2 cancels here, and a 3 and a 19 and a root 3. Okay, so that's my exact value. This is the application problem, right? So we come down to how many pounds of pressure that we have. So 7 million and some change, very close to 7. Okay, so thank you guys. I'll see you on the next one.